Welcome to episode 36 of Cooking with Unity. I'm your host, Maximilian Moreau, and with me is my tech, Philip Wilson.
It has been a little while.
Yes, it has. It was the holidays. How was your holiday?
It was good.
It was good. I actually knew this before I asked this time because this is the second time we're actually recording this due to some problems I had on my computer due to reformatting it. Anyway, I had a good
difficulties.
Yeah, little technical difficulties. But yeah, so let's get. I had a good holiday too. Hope everyone else out there had a good holiday, and let's get started on this. So this week we're going to be handling pathfinding because I've had an overwhelming demand to show off how pathfinding works. And so I've got this little test case here. Whoops, I don't need to hit play on it because it's just a script that I conjured up that uses Dijkstra's algorithm for pathfinding, so it will highlight the shortest path in green. It's kind of hard to see because it's also highlighting them in white. But see, that's the shortest path, and if we move this closer, that becomes the shortest path, and this is now the shortest path because the other two are far away. Anyway, we're going to be setting this up, and so it's going to be a little bit more technical than we usually do on the show. But it's not impossible, and I'm going to walk you guys through getting this thing set up, and we're basically going to just take pseudocode for Dijkstra's algorithm on Wikipedia and implement it in C# and set it up in Unity. But before we do all that, I'm going to open up our old project. We have a couple things that I want to get done real quick, so don't save, I don't care. So here's our little FPS setup here. What we had last time is we have the ability to move around, we have the ability to shoot, and you can go up to these walls and they open up, and then our little monster follows us around and you can shoot at him.
The terrifying
green cube, and he looks at us no matter what angle we're at whatever speed we're at. So we're gonna fix this up a little bit. Actually,
he's kind of looking a little bit.
I can jump over him because he limbos.
He's looking a little bit like one of the tentacles from Day of the Tentacle. With the
with the bullet holes. Maybe if I get a couple more in there,
like one in right in the middle. There you go.
Yeah.
Yep. Now it looks more like the tentacle from Day of the Tentacle. Wow, he's dancing.
Yeah,
now.
he can just ninja move.
Oh
yeah!
Wow! Oh wow!
Whoa!
Oh wow!
All right,
that's awesome.
Anyway, so we're going to make it so that he moves towards you, but not looking in the direction of you. And then also we're going to make it so that he has a turning radius, as opposed to just having it so he always faces you instantaneously. We're going to do this really quickly because some people asked about it, and it's pretty easy to set up. So, first of all, we're going to make him look in your direction, but not in your direction on the y-axis. So
we're going to make some assumptions about the world, like basically that it's on a flat plane all the time, correct?
Yeah, exactly. So to do this, we're going to make the assumption that Y is always up in our world. We're not doing any Mario Galaxy stuff where we're on planets that have different orientations and stuff. So that requires a whole different set of assumptions and logic. This one's just going to be, we're just going to take the direction towards the player, get rid of the Y component, call it good. So what we're going to do here is I'm going to add another vector 3 here, and this one's going to be player direction equals, and we're going to basically just do the player position minus transform position.
Oh, you got layer position.
Yep, it happens.
Yep.
Thanks for the catch. Now, now that we have our player direction, we're going to adjust the player direction dot y to 0.0f. And then our normalized player direction, we're going to just take player direction dot normalized. So once we've made these changes, we should be getting the monster moving towards us, and it should not care about the y-axis anymore. So if we jump up, it no longer follows us, so that's good. And it's still following us in the horizontal aspect. So it's doing everything exactly the way we want it to do it right now. The reason the facing is working is because we're using the normalized player direction for the facing here. So now let's add a public float turn speed. I'm going to set this equal to 30.0f to start with. So that should represent 30 degrees per second of turning. So instead of just setting the transform rotation to our normalized player direction, we are going to use function to do this, and I don't actually remember exactly which one, so bear with me here. So quaternion, I think it's under quaternion. Dot look rotation. No, that's not what we want. That's what we're currently using. Transform dot rotate around local. That's not what we want either. Vector 3 dot rotate towards. There we go. This is the one we want.
There we are.
So vector 3 rotate towards. That's not one in transform dot position dot rot. Yeah. Okay. So yeah, it's just in the vector library for whatever reason. So vector 3 dot rotate towards. It takes the current vector, the target vector, and the max radius delta. So rotates towards the current is our current rotation. So it would be look rotation returns normalized. Okay, this actually just returns a quaternion. This one actually returns a vector 3. It's a little awkward. Whatever. So our current vector would be transform dot forward. Our target vector would be normalized player direction. And max radians delta and max magnitude delta. I swear there was one that took a maximum quaternion dot look angle axis Euler from 2 rotation.
Well, that sounds...
No, it's still not good enough. Here, let's see if transform dot rotation dot rotation. Alright, I'm gonna cheat.
Can we do like a slurp or a lerp?
We could. It's not necessary though.
Okay.
Let's just see what I did here. I cheated. I actually did do some work outside of an episode, believe it or not. So
is it from 2 rotation? Quaternion from 2 rotation?
it doesn't have a rotation rate.
That's a good point.
So, zombie AI, let's see what this says. Quaternion dot rotate towards is what we want.
Huh.
Okay. Sorry that took me so long to find. So
Well, that makes sense.
Quaternion, I swear I found that one. Rotate towards. Okay, yeah, this is the one we want. Okay, so from to, so the from is our current rotation. So transform dot rotation. And 2 is our quaternion look rotation player direction here. And our max degrees delta is turn speed times time dot delta time. And this actually returns something, so we need to actually set the transform dot rotation equal to this.
All right.
So let's see if this works. Did I somehow close? No, I didn't close the project. All right. So we hit play, and now if we open up our little monster closet here, he will rotate. Oh, that was fascinating.
Yeah, that's kind of odd.
Okay, so that reanimated and hit him really hard. Let's change something on the monster real quick. We're going to go into his physics here and make it so that he freeze position, freeze rotation. We're going to freeze the X and Z components here, and that'll at least make him a little bit more stable.
So now he shouldn't be able to fall over.
So he shouldn't be able to fall over, and he should still be free to rotate towards us.
No, he's certainly rotating towards.
Yes, he is. And so now he gets kind of a curve to his... Oh, wait, no, because he's... Okay, so he's still moving directly towards us. We're going to change one more thing here. But he's rotating at a slower rate. So the rotating is working. So the only thing we're going to change now is we're going to go into... we're going to make it so that his position isn't towards the player. His position is just going to be forward. So it's going to be position plus equals transform.forward times speed times delta time dot delta time. So now you'll see that he'll have a little bit of a wide turning radius now when he tries to turn towards us.
Which is more what you'd expect.
Yeah. So he keeps traveling in his forward direction, so he kind of has this circle. So we could probably get in the middle of him and have him rotate around us perpetually because we have a really long turning radius. But if he starts looking directly at us, he'll start going directly towards us. So
it's pretty cool.
And if you want him to be a little bit more responsive, we can just change his parameters. We can go in here and be like, instead of the turning radius, where it says AI, there it is, not the AI. We can make the turn speed, 90, and he'll have much tighter turning radius. So let's see how this looks now. See, now it looks like he's just facing us, but if we can scoot by him, he'll rotate around. Kind of has a Dalek feel.
Yeah, a little bit.
Yeah. Exterminate.
Exterminate. Exterminate.
I should put a little plunger on the front of him. Sometimes that's all you need for art is add a plunger. So.
Oh, there you go.
So just trash can plus plunger equals art. So.
Equals Dalek.
Equals Dalek. And Daleks equal art.
That is true.
Although they'd probably disagree with you on that.
Oh.
So now we have the monster moving and turning the way that you'd expect. So we've spent probably more time on that than I really wanted to spend, but that's okay. Mostly because we couldn't think of the words rotate towards. I haven't memorized everything in the documentation, obviously, and if you're looking to do something, always just search online. There's usually 12 different ways of doing things, so keep that in mind. This one is one of those 12. So now we're going to work on porting Dijkstra. And as I said, this is going to be a little different than the show usually is because it's going to be less interactive at this point. We're going to basically slog through porting some pseudocode into C#, and then hopefully we'll get a little test case that we can show off.
Absolutely.
So let's do that. We're going to start a new script. I'm going to call it Dijkstra.
Yep.
Algorithm. Algo-R-Y-T-H-M. Algorithm. There we go. Can't spell worth a dang. Probably still can't.
Yeah, I can't either.
Oh, no, they don't use a Y. They use a I.
Yep.
Right.
Dijkstra.
It's not like rhythm, it's like rhythm. I don't know. And let's reopen this. So, first off, this is not going to be a mono behavior. This one's going to be just a class. And we're going to basically just be making one monolithic function. We may add more helper functions to this later, but it's just going to be the Dijkstra algorithm. So, the algorithm we're going to be using is Dijkstra's algorithm. It's a node traversal algorithm that basically determines the shortest distance between two given nodes. And this is an example showing it if you have a whole bunch of nodes, how it gets around an obstacle and gets to the goal here. And it does all this very, very fast. It does take computation to do this, each iteration, but it's not so much... Like, computers do thousands and millions and billions of things every second, and you don't even know it. And so this is an example of doing a whole lot of things to find an optimal path. And so once it finally gets to the goal here, it chooses the lowest cost path here. So here is our pseudocode, and this is just right on Wikipedia, and I implemented this today, so it does definitely work when converted into real code. So what I usually do when I'm porting from any language, whether it's pseudocode or Java or whatever, and pseudocode is not a strict language, just so you know, it's just a way of describing things in a code-like manner. I just copy and paste them into where I'm going to use them. I do a little comment thing there, paste them in, and then do another uncomment thing. And that way it doesn't upset monodevelop in any way.
So I have a quick question.
Sure thing.
Why did you take the mono behavior off of that? What difference does that make?
The difference that makes is, this is a good question. This is not going to be attached to any game object and cannot be attached to any game object. So this is not derived from an object.
Okay.
So this is just going to be a class that we are going to reference a global static function that just has this algorithm in it. As I said, we may add more helper functions in here, but it's kind of like mathf is a class. When you type in mathf, this is actually it's a struct, evidently. Structs and classes are very similar. These things are members of the structure and stuff, and so we're going to be doing the same type of thing. It's going to be like Dijkstra Algorithm dot whatever. I'm probably just going to call it Dijkstra because this is what it's called down here. So
sounds good.
So
that
here we go.
Answered my question. Thank you.
No problem. So I'm going to get rid of the start and update because those don't mean anything if you don't have a monodevelop. I mean, you could make start and update, but they're not going to be called at any time unless you call them. So so here we go. I just go a line at a time and just kind of copy paste and then work it into something that's right. So in our language, we don't use a colon at the end of a function declaration. We would do an empty brace thing here. We don't use the term function. We would use void if it was going to return nothing. But it's actually going to return something. I'm going to actually just leave it as void for right now. And then we actually need to type our things here in C#. So this graph has to be a type of something. So we're going to call this a list. Okay, so yeah, actually, I'm just gonna power through it. So we need a graph and we need a source, whatever these things are.
Okay.
And so you can look down here and kind of figure out what these things are for each vertex v in graph. So the graph needs to contain vertices. And the vertices, if you look down further, they need to contain neighbor information. So for each neighbor of v of u. So we need to have this neighbor information, and we need to have position information. That position is used for the distance function here. So before we go any further, I'm actually just going to comment this out so that monodevelop doesn't get mad at us. We're going to create a new C# script called node. Probably should be more specific, but I'm just going to go with node for now. And this node is going to be a mono behavior. We're going to be attaching this to objects to represent the node graph and the individual nodes within the node graph. The node graph is the sum of all the nodes in the scene, and the nodes themselves contain the information on what they're connected to adjacently. This will make sense as we fill things out here. Mm-hmm. So because we're doing mono behavior, this is going to be attached to a game object. That means we already have position information. We have the vector3 transform.position. Mm-hmm. So we don't need to add position information, but we do need the neighbor information. So I'm going to create a public game object. We're just going to use the most generic thing we can for right now. We can make it more specific as we go along, though we're not going to need to. Public game object neighbors. And this is actually going to be an array. And that's all we've got so far. That's all we need for our node so far. So I'm just going to leave this as is.
Yeah.
So that means we now have a node class. And though we're going to be working with them as generic game objects for right now. Part of the reason I'm doing this is because when I tried doing it as a node itself, I ran into some problems. I'm not sure if it was on Unity's end or if it was on my end or if it was a problem that got fixed while I was working with it. I'm just afraid to actually do that here. So this is partially some forward-looking stuff that I'm doing here just from my experiences earlier. I spent about 3 or 4 hours earlier messing around with this stuff. So we have our Dijkstra, we need a graph, so we're going to just have this be a list of game objects. So first of all, we're going to be using a few different data types. So we're going to do using system.collections.generic. This contains a whole bunch of really useful things, including lists, dictionaries, hash tables. There's probably a few others that I can't think of. Queues, all sorts of fun little toys, stacks. We're going to use a stack on this one, actually. And they're just different data collections. An array is a very specific type of collection, like the one we used here. And these are not mutable, meaning that if you want to have a new array, if you want to add something to an array, you have to basically create a new array with that new object in it, and then you replace the existing array. A list allows you to add and remove at will, and handles all the sorting and stuff for you.
Yes.
And so we're going to be using that for a few things here. So
a list is a mutable array.
Yeah, in the most basic sense, it is a mutable array. Yes. So we've got this graph. So we're going to call this a. I'm just going to use the exact variable names that they use down here so that we don't get ourselves confused. That means that we're going to be breaking some of our protocols here because already graph should not be uppercase.
Yes.
But we're going to stick with that for right now just till we get things implemented. And then we can do find, replace, and stuff and just refactor things.
Sounds good.
So our graph is actually going to be a list of game objects. List game object graph. Actually, we don't even need that. We don't need a list here. Let's just do game object graph. So this is an array of game objects. We're going to need a source for right now, and this source is just going to be a game object that we assume to be a node. So game object source. So we've finished line 1.
Yes.
As I said, this is kind of an involved process, but it's not terribly difficult. So for each vertex v in graph. So for each is one word in our language. We need to put brackets or parentheses around here. We need to get rid of that little thing. I'm going to go ahead and fill out the empty case here for us. And then, so we want vertex of v, so we're going to just say game object v in graph.
All right.
So that's line 2. That was an easy one.
Yeah.
So dist v colon equals infinity. So the colon equals is actually a fancy way to do assignment. Someone who was writing this pseudocode probably was used to older older programming languages that assignment is more specific than equals in a lot of languages, in a lot of the older stuff. Nowadays, we just assume that equals means assignment and double equals means comparison. So, this we can get away with just doing an equals. Now, infinity is not a real thing in ours, but we have an equivalent. We have mathf.infinity. So we put that in instead of infinity. And then we need to figure out what this dist thing is. And dist basically takes a game object or node and gives you a value, and it takes a value for the node. So this is actually a dictionary is what we want for this. What a dictionary is it has a key, which can be any type of object, and it has a value, which can be any type of value. And when you insert a key, you insert it with a value, and if a key, if you reference a key, you get that value back. And so what we're going to do is, at the top here, before for each, we're going to declare it. We're going to do dictionary, and we need our type. So our key is going to be game object, and our value is going to be float. It's going to store a distance for us. We're going to call it dist, just like our function, our thing in here is called. And we're going to go ahead and initialize it as a dictionary. So new dictionary, just autocomplete that, and then put these little brackets at the end. So this is now a functional dictionary. So dist.v equals math.infinity. So this sets, for each game object, it adds it to our dictionary and sets all of the values to infinity. Yeah. In a dictionary, you can have you can only have one key per value, but you can have multiple of the same value on different keys. And so we're going to have multiple of the same value of infinity on all the keys right now. So additionally, we need to do oops, what did I do there?
I accidentally deleted it.
Yeah, there we go.
Thank God for undo.
Yeah, seriously. I don't know. Actually, I remember what it was like before undo. It was terrible.
Yes.
So now we have a previous v equals undefined. Actually, I've been copying and pasting. We should copy and paste.
Yep.
So previous v undefined. So undefined is the same as null in our language. We don't need this colon. And we need to define our previous thing here. So previous is the previous node in optimal path. So this is actually going to be another dictionary, but instead of a dictionary, this game object comma float is going to be game object comma game object. So this references
The parent game object.
it's basically like a parent.
Yeah.
It's a connected. What this thing is going to basically spit out is a list of nodes to traverse to, and so this represents the previous node that's connected to whatever node that we're looking at. So all we're going to do is I'm just going to copy this, and then we're just going to change some things around. So this is game object, this is game object, and then we need to name it previous.
All right. Pseudocode seems daunting at first, but I think once you take it bit by bit, it's not so bad.
Yeah, it's not. And the thing is, like, what I want to illustrate here is, like, I basically know how Dijkstra's algorithm works, and you can read up on it, and it makes sense logically once you work into it. But you don't really need to know how something works to port it. You can just kind of start hacking at it.
Mm-hmm.
And you'll learn how it works as you do it. So it's actually usually a good practice if you run into code. Like, this is something that I want to stress. Like, if you run into code that's in JavaScript and you've been watching only my show and you only know C# and you're really kind of worried about JavaScript, it's 10 times easier to port to this than what we're doing right here. And what we're doing right here is not that complicated. It just takes some time. And it takes a little bit of knowledge. Like I knew about dictionaries and stuff, and so I'm kind of front loaded on this, but you just kind of feel through this stuff, and you just need to figure out what types you need. If you're dealing with JavaScript or Unity script, you may have to do that a little bit too, because you don't necessarily have to say what type it is, but it'll be more obvious because it has to be some type eventually. So
yeah, I was just looking at A-star stuff earlier today, and I mean, it's a little bit more complex than Dijkstra's, but
yeah, I went with Dijkstra just because it's a little bit easier to work with. A-star is a more general case and actually is very cool and has a heuristic aspect, and so like it chooses a direction that's appropriate first. It doesn't just go out to all nodes. This one just goes out to all nodes.
In this case, I think Dijkstra's is the better option. So
yeah, and we could always change it up or change it up. The only thing that we want here is we just want something that takes our source and our target and gives us a path. And so we don't care how it does it, as long as it does it fast enough that it's useful. So so now distance source. Okay, so dist source equals 0. I didn't copy it first. I should have done that to be more specific, but I just took this line, dist source equals 0. All right, Q is the set of all nodes in graph. I think they called it Q because they wanted this to be a queue. We're actually just going to make it a list. So it equals the set of all nodes in graph. This would be great if there was just a way to, well, okay, so is equals the set of all nodes in graph. We've got the graph there. So Q can just be the same as graph. So we can just call this game object Q. Actually, we're going to do a list.
Are we?
Yeah, because we want to be able to remove stuff from it easily here while Q is not empty. So this is a clue that means that we want it to be mutable. So what I'm going to do is, since we're already going through all the game objects V and graph, we're going to set it here. So we're going to create a new list. So list game object. This is going to be called Q because we're just going to keep it consistent.
Yeah.
Equals new list game object. And we need to put these, otherwise it will complain at us. Because this is actually a creation function here. It just looks really awkward to have those next to each other, but that's how it works.
The braces, or not the braces, but the carrots next
to
the...
So now we're just going to add to Q, Q.add v. So it looks a little different now than the code before, but this basically sets up this incredibly loaded line here. The set of all nodes in graph. Yeah. That's what this is meaning here. It's the set of all nodes in graph. So go on to our next line. So while Q is not empty, so this is going to be while Q.count is greater than 0. That means it is not empty.
Yep.
We need... Okay, so U is the vertex in Q with the smallest distance in dist. So this is another incredibly loaded statement.
Yes.
So we're going to have to find out which one has the smallest distance. Now, there is going to be one with the smallest distance. Here we've set everything to infinity, except for our source one is 0. So this one's going to be the smallest distance. We're not going to assume that. I'm just going to iterate through everything on the list, pick the smallest one. So this is going to take a few lines of code, even though it's only one line here. But it's pretty easy to follow. So for each object in Q, so game object in Q, we're going to check the distance. So we need to have a variable here. So I'm going to do float shortest distance equals mathf dot infinity, and game object nearest or shortest distance node equals null. So if dist obj, so this gets our distance from the object, or from our little distance dictionary.
Mm-hmm.
So if dist obj is greater than or is less than shortest distance, we set shortest distance to equal dist obj. I'm not doing any optimizations or anything right now either, and we're probably not going to touch on that today, but we might if we need to later. And then we set our shortest distance node to obj. Oops. So what this will do is it'll go through, it'll find one, and it'll be like, is it smaller than the shortest distance? So let's say it finds one of our infinity ones first. It's infinity is like, nope, it's not shorter, so it just skips those. Nope, not shorter, nope, shorter. Say it found one that said 10. It doesn't have one in there that says 10, but it goes in, it's like, okay, 10. So now the shortest distance is 10, and the shortest distance node is object. And so then it goes on and finds an infinity, it discards that one. It finds a 30, it discards that, and then it finds a 0, and it's shorter than that, so it sets the shortest distance and then resets the shortest distance node. Mm-hmm. So what you get at the end of this is shortest distance node is the node with the shortest distance.
Yeah.
And that's what we want here for the vertex in Q with smallest distance in dist. That's what this represents. So since they use U, we're just going to do game object U, and then we're going to set it to our shortest distance node. And so now that represents exactly what they want.
That represents that one line.
Yeah, this represents all of this represents
this one line.
This one line. And this is where it kind of gets dicey on things where you have to kind of figure things through, but that's why it's pseudocode. It's just people typing in whatever they want. Pseudocode doesn't have to work. You just have to type it in.
It's just theoretical.
It's the theory, yes. So we have our shortest distance, so we remove U from Q. So that's just going to be Q dot remove U. If dist U equals infinity, or is equal to math f dot infinity, in this case we break, so that's these lines here, and then end if is just the end thing here. Why is, oh yeah, I didn't put a semicolon.
You gotta watch out for the
So break will break us out of the while loop. I don't actually know exactly why it's doing that there, but I'm sure it's important. I'm not going to skip any steps on here because I'm imagining the Wikipedia people are pretty good about not having stuff you don't need in these things. So so now for each neighbor v of U, so for each, so we need the neighbors of our node. So for each game object neighbor, okay, so the game object v in u dot, so now we need to get our node stuff. So we need our node class, which we can get by doing get component node, and then we have to, that's actually a function, so we do that. So this represents for each neighbor v. Oh wait, no, sorry, this isn't the neighbor yet. That's just the node. So dot neighbors. There we go. So this gets us all our neighbors. And so float alt equals dist u. Yeah, I'm actually going to copy it. I don't know why I alternate between doing these. I guess sometimes it's easier and sometimes it's not.
Yeah.
I'm just going to do it this way. So I added a float here, so we have a type. So float alt, we want equals, and then we have this arbitrary looking function distance between u and v. So what this represents is u minus u dot transform dot position minus v dot transform dot position, and then we so we need to add those two. So distance between, so this is not the distance, this is just the vector between them. The distance is the magnitude of these two vectors. Magnitude just means distance, effectively, in the case of a vector. It's the length of the vector, and so if you have a length of vector, that represents the distance between the 2 points. So, I tried doing square magnitude before, and it didn't actually work perfectly. I thought it would work because we're comparing distances, but we're doing something that makes it so that optimization doesn't quite work. So now we do if. So I'm going to just copy and paste this in. If alt is less than dist v, so we just do that. Dist v equals alt. I'm just going to actually paste all these in. Actually, I'm going to do it one at a time, though, just because all of them have bad indents and stuff.
All right.
So, and actually, I mentioned earlier that they wouldn't have anything extra that we don't need. There actually is an extra thing in here. I remember running into it.
Oh, yeah?
So dist v equals alt. That's an easy one. Previous v equals u. That's another easy one. Didn't have to do anything but delete things there. Decrease key v and q. So this reorders the queue. This would assume that we're doing a priority queue type setup. Mm-hmm. We're not. So we're not even going to worry about this. This would technically, if you did it right, it makes it so that iterating's faster. Mm-hmm. We're just not going to worry about it right now. So end if, end for, end while, return dist. So I'm not going to deal with the return thing because this is not actually the complete solution just yet, because there's this little extra group here. Because basically, here's this caveat. If you're only interested in the shortest path between vertices, source, and target, that's exactly what we're interested in. We can terminate the search at line 13 if u equals target. So we're going to basically throw this stuff in here somewhere. I'll show you that in a second. We're done for now. So when I said a second, I actually really meant it. So this doesn't do anything yet. It just does some stuff. Now, we want a target. We don't have that currently because their implementation didn't include one. So we're going to have a game object target. And then we're going to paste this in just like we've been doing before. So, and then I'm going to go ahead and just for the fun of it, I'm going to paste this text here as well, just so that we have it for reference. So we can terminate at search at line 13. So line 13 is remove u from q. So I'm going to do it just after the removal. It's kind of vague on that. I don't think it matters either way, but we're going to do it just after the removal. Because if you found it, it doesn't really matter if it happens before we remove it or not, but I'm just going to do it after.
Yeah.
So just going to paste this line in. So S equals empty sequence. So I have the advantage. Check to see if we made it to the target. So this is not actually the first line because it says we can terminate the search line if u equals target. So this is actually pseudocode in the form of a sentence here. If u equals target. We actually do want that.
Do you want a comparative equal then?
Thank you. If u equals target. It probably would have gotten mad at me.
It would have
might
just
not have.
slightly. It
wouldn't have been mad enough.
It
should
thrown
be.
out
It should
an
be.
exception.
It should be extremely mad.
Yeah, it would have just thrown out an exception.
Older ones don't. They just assign it.
They're just like, oh, it's
Oh,
equal.
this is an assignment, and then it returns 1.
Yeah, it's like,
That's,
it did it!
That's the worst thing in the world.
Yeah.
It's just horrible when you're debugging it. I'm glad that they're just like, I don't think you meant this. Like
Yeah.
C# is like, nah, I don't think you actually want to do that.
You don't actually want that to be the case.
So, S equals empty sequence. So what we're doing here is insert U at the beginning of S, and then, so we're inserting things at the beginning. So what this is, and the reason they called it S is because this is actually a stack. And this is one of those things that the benefit of using things long enough, you'll notice these patterns. Mm-hmm. What they want is they want to basically push things into a stack and then pull things out of the stack in the order. So it's the first in is last out in this case. So the first one you push in is the last one that you're going to pull out. Mm-hmm. And so the reason they call that a stack is if you have a stack of papers, it is exactly that. When you put a piece of paper down, if you were to put another piece of paper on top of it and another piece of paper on top of that, the last piece of paper you would pick up if you were picking them back up in order is the bottom one.
Would be the first one.
The first one that you put in. So first in, last out. So stack S. Actually, stack when we need to type. The type is game object, and we want capital S. Equals empty sequence. So equals new stack game object. So that's already an empty sequence right there for us. And we need our little brackets there.
All right.
So that's that line. Then while previous U is... Oh, wait. U equals target. So U already equals target here. So I'm not going to bother. Because U has to equal target to even be in there. So I'm just going to ignore that one. You could put it in there, it wouldn't hurt anything, it's not necessary. So while previous U is undefined, so while previous U equals null, let me put the braces and do all that wonderful stuff.
Yeah.
The parens, I always say the wrong word for that. So while previous U equals null, so we already have previous U, right? Yeah, we do. We have previous. So that's part of our structures here already. Insert U at the beginning of S, so that's S dot push. So stacks use the term, instead of insert or in Q or add, they use push and pop. Push means add something to the stack, and you specify an object. Pop means give me the last thing off the stack, and it doesn't even take anything. It just gives you the last thing. And it actually removes it from that stack too. So, so S dot push. S dot push U. That's what they want, right? Down here. Insert U at the beginning of S, and then U equals previous U. So this actually does matter. So U now equals previous. So this is basically traversing up that path that we have found so that we're going to have all the nodes in order from beginning to end of how to get there. So we have that stack.
Let's just end the while.
And so let's, at this point, we're going to take our... So at this point, our thing should be complete. This thing has successfully done what we need it to. Mm-hmm. We're going to finally return something. We're going to return our S. So now we know what our return type is going to be. It's going to be a stack... stack of type game object, and we're going to make this a public static. So now we have, this is probably the most complex looking function we've ever declared. All this means is it's public, so we can access it anywhere. It's static, so that means we can access it without having an object reference, which is convenient. We've got, it returns a stack of game objects, and it takes a game object array a game object source. This game object array represents all of the nodes in our scene. Or we do a subset of nodes too. You could just send in, we don't care about this part of the level yet, so if you wanted to optimize it, you could do that. And then this represents a source object, and this represents a target object. So if I hit save here, there's going to actually be one complaint, I think. There may be more than one complaint. Let's see if we get any complaints. Console. Yes. Not all code paths return a value. This is what I was expecting to get. So what this means is we have this return S here. It's possible, if it's not possible to reach the target, return S will never be called. Because you cannot equal the target if it can't be reached. It just, the way it will traverse, it will not actually reach the target. And so in that case, we need to still return something. So I'm going to return null. So we can check for null when we use this function, and that determines that we haven't found anything. We'll be adding those checks later as we progress. So now we have this huge chunk of code and no way to tell if it works yet. And this is the one problem with doing this kind of thing. So now we have to actually find a way to do it. So I'm going to basically be setting up what we did, what I did earlier. I showed you with those little node things, and I'll show you how we can get that set up. So first of all, we're going to make this node class a little bit cooler. So we've got our neighbors here. We're going to make it so there's a function called void onDraw Gizmos, and what this is an editor function that it doesn't require you to be in the editor namespace or anything, but this function is called for every object in the scene that has this script on it. It's called when it's supposed to draw something in the editor space so that you can see some stuff. So I'm going to first just start by having it draw a cube where the node is, so that way we don't have to attach a renderer or anything to the nodes, but they will show up nicely in the editor.
This is exactly what you were showing us earlier, where you were dragging it around within
yeah,
the
exactly.
editor.
We're going to make that part work, and that at least shows that it works.
Yes,
and
absolutely.
then if we have time, I may go a little bit over to actually make our monster move using the node graph.
Yeah.
We'll see how it goes. So on draw gizmos, we're just going to draw so we do gizmos dot draw wire cube, and this takes a center and a size in both vectors. So our center is just going to be transform dot position, and our size is going to be vector 3 dot 1. We'll just make them a cube that is 1 unit for now. So if I go ahead and I'm just going to kind of go above the scene here and rotate around, and we're going to create a empty game object, and we're going to call this a node, and call it node 1, and we're going to attach our node script to it. So now you'll see, I'm going to focus on it, we have this little wireframe cube. It doesn't have a cube renderer or anything, it's just drawing this in the editor, and this thing will not show up at all when you're playing. Actually, that's not entirely true. If you have gizmos enabled when you're playing, you'll see it. So, like, if I was to move this into our scene somewhere, hit play, I won't see it anywhere, but if I hit gizmos here, it should show up if I put it in a position where it can actually be seen. I did, but maybe I'm wrong. So let's see. Yeah, there it is. So there's our little node. But if we turn off gizmos, it will just disappear. So that's good for debugging purposes. You can see our light there.
Yeah, the
we
light
can see
source and everything.
And things like that. So this is super useful from an editing standpoint. And we're going to make this next episode, I'm going to focus on actually making this more easy to edit. You'll see that this is kind of what's the word? It's not a long process. It's a tedious process to link up all these nodes right now, and we'll make the tools a little bit better next time. But for right now, we're just going to do it kind of manually using whatever tools we've got in Unity, which are good tools. So I'm going to just move this out of the scene just so we don't have to worry about the scene for right now. And so we've got our node, and so I'm going to create a new node. I'm going to duplicate this one. I'm going to call it node 2. And we're going to move it up here. So now what I'm going to do is we're going to go in here and gizmos.draw line, and we're going to take the from is going to be transform.position, and the to is going to be to our neighbors. So for each game object neighbor in neighbors.
Those will just draw a line.
So this will draw a line between all the object and all of its neighbors. So draw a line, transform to position, and then neighbor. And it's not auto-completing for me, but
yeah, it just needs to compile.
Transform position. It figured it out from there.
Yeah, I don't know.
All right, so
At least it figured it out.
and I'm going to also make it so that we can kind of tell the direction that it's going. There's not a real good gizmos.draw arrow. I kind of wish there was a draw arrow, but there's not. So we're going to draw a sphere, a small wire sphere, at the neighbor's location. And I'll show you why we're doing this in a second here. So neighbor.transform.position, and then the radius we're going to set to 0.25 f.
Oh, you need a paren.
And I need a paren. So now it hasn't changed anything yet, but if we choose this thing and actually drag node 2 into our neighbors, you'll see it now has drawn a line and a little sphere inside this. Now the reason I did that is because technically these links don't have to be bidirectional, and this is actually an advantage for us because it means that you can create more complex behaviors for things. But basically, you can make a one-way connection.
Yeah.
Generally, we're going to want two-way connection, so I'm gonna basically draw this thing into his neighbor, and you can tell that it's been connected both ways because there's now a sphere in both of them.
Yeah, it looks
That's
like
the reason
a
I did
barbell
that.
now.
Now the problem is, of course, if you have multiple things connected to multiple things, you're going to already have spheres there, and so you're not always going to be able to tell if it's connected properly. Mm-hmm. We may do some stuff on the next episode where we colorize it or make it so that you can see which ones it's connected to when you've selected the thing, but we're not going to worry about it for right now.
All right.
This is just for our personal visual stuff. So let's go ahead and create a few more nodes. I'm going to actually just kind of create the same example that I had before. So node 3, we're going to put over here. I'm going to duplicate it again. And node 4, we're going to put down here. So we're going to... So why did this stop drawing this? Oh, wait, it's only connected to 4. Oh,
it's
because I duplicated
it.
So that's what happened. So, so we don't care. We want this one to not be connected to 4, so I'm just going to delete that. Although that still...
So now they're all connected to that one.
0. Just no neighbors. Okay, so they are connected to that one. Okay, so yeah, let's just 0 out all of these. Alright, so none of them are connected. So node 1, I'm going to connect nodes 2 and 3. And 3. Node 2, we're going to connect to nodes 1, 3, and 4. So this will be a little cross connection thing here. And then node 3, we're going to connect to 1, 2, and 4. And then the final node here, we're just going to connect back to
2 and 3.
2 and 3, thank you. I was just about to do 1, 2, and 3. This creates a little interesting structure that's easy to tell if we've got a different distance and stuff. Yeah. So that's the reason I set it up this way originally. So I'm going to go ahead and save scene because we haven't saved in a while. Variable neighbors of node has not been assigned. That was probably because there was nothing. Okay, so that's actually because... Oh, that was because we had... that was the time that I deleted one from the list, but it still had something in the list, so it was an undefined thing. So just ignore that for now. So I'm just going to play and then hit pause again just to make sure it looks like it's all looking good. And so everything's looking good. So now we're going to actually need to draw the goal. So what I did for my debug test, and that's what I'm going to do here, is I created another game object here called goal. And so if there's a goal, if goal, then we're going to attempt to Dijkstra path to that goal from this object, and we're going to do it in a green path. So we're going to do the Dijkstra algorithm. So we're going to call this function as Dijkstra Dijkstra algorithm dot Dijkstra, and we need the graph. So the graph is going to be all the nodes. So what I'm going to do is I'm going to cheat a little bit. We're going to select all these things. We're going to go to tag, add tag. We're going to create a tag called node.
Oh.
And then we're going to reselect all these things again and actually tag them, which gummed me up real good last time. I always forget to tag things. So all these things are tagged node. Looks good. So for all the nodes in our graph, now all we have to do is just do GameObject.get find GameObjects with tag node. So this represents our graph. So that's our first parameter there in our function. So our next parameter in the function is the source, which is just our current object, so GameObject. And the target is our goal. And so this will return a stack. So we're gonna grab using system.collections.generic, and we're going to just do stack path equals Dijkstra algorithm. So now all we have to do from here is for each game object in path, we're going to just draw from, I'm going to need another variable here. What is it called? Game object current equals game object. So for object path, we draw from current, so Gizmos dot draw line current, and then the position. Okay, so current dot transform dot position, and the object dot transform dot position. Alright, and then we set current equals obj. So I'm gonna make the lines green now. So Gizmos dot color equals color dot green.
Oh.
So hopefully what this will mean is if we choose one of these and we set the goal, so let's set the goal to be, stack game object dot path. So not dot, but
yeah,
we need to have the actual type there. So did that fix that? Okay, cool.
It did.
So we're going to go here. We're going to add node 4 to there. And did it work? I do. No, that's just the green from the vertical there. All right, so goal is node 4. So that didn't do anything. I'm gonna hit play and then not play.
Huh.
All right. So that
I'm not seeing
didn't
green.
quite work. So Gizmos that color equals color green. Draw a line. Current dot transfer to position. Obj dot transform dot position. Current equals obj. All right. Let's just do something else. Let's draw a Gizmos dot draw. Let's draw a wire sphere this big.
Just so we're making sure that this is working.
because I might just have something wrong. Transform dot position. Actually, no. Object dot position. Position. Dot transform. Dot position. And then the radius will make it 1.0 f, so it'll be a big old sphere. So let's try this again. I'm just going to hit play and then not play again. Alright, so
something's going wrong somewhere.
If goal Alright, so we're probably not getting what we think we're getting out of this, so let's do a debug.log got here.
So we're making sure we're even getting in there.
And then I'm going to also do a debug.log, and hopefully we can get some information out of the path.
Alright, let's see what happens.
So now I'm going to go to console.
It got there.
Got here. So generic stack. So it is actually a stack. That's good. That means it's not null.
Oh, sorry.
So for some reason, I have a feeling if we do one here, let's see, debug.log, here also, with an exclamation point. So I'm going to hit play, and then I'm going to not hit play.
It did not get there.
No, I did not.
So why didn't it get there? That's the real question.
So this stack is empty for whatever reason. So stack equals previous u equals null, return s. All right. So let's throw some debugging in here. I hope this doesn't end up being one of those really weird ones, because I had one earlier that I didn't actually figure out what I did to fix it. And
Oh,
it
that's
just fixed itself, which is always terrifying.
Yeah,
so.
that is terrifying.
So let's see what we got. I'm going to go ahead and you can now in Unity 4. Evidently, this is a new thing. You can actually debug your editor scripts. So
Really?
we're going to give that a shot. So we're going to go in here, and I'm just going to see if we get to a target at all. And we're going to connect in, attach, and then we're going to go over here, and it should just immediately break. Okay, so it did. So stack, okay, so previous has 4 things in it. These are variables here, so previous is kind of a complex little thing here because it's a what type is it? It's a list, I think, or a dictionary. It's a dictionary.
It is a dictionary.
So previous u equals null. Oh. Well, previous u does not equals null, I think. Hold on. Let's see. While previous u is defined. Okay,
so if it's not null.
Not equals null. That's where my problem is. This will probably fix it right here.
See, that's good though that we find that out.
Yeah, exactly. This is the reason that we have debugging capability. And there we go.
And
it drew
worked.
it, and it drew the big
circles
too.
So that was it. It was just a
yeah.
double
So
equals null.
let's go ahead and get rid of the big circles because we don't really need those.
Well, I kind of got attached to them already. I'm joking.
All right, fine. If you're attached to them, at the very least, we're going to put the color ahead of them so that the first one isn't white for some stupid reason.
Okay.
We'll do it here.
It's just exciting.
All right. So now we should have. Yeah, there we go.
Yep, there they are. They're green.
So now
circles.
if we move this around, it will automatically update whichever path is shortest.
It's pretty
Joy
awesome.
of joys. All right, so we now know that our algorithm works, and it actually did not work until we tested it.
And that's why
fixed
it's good to test these
which
things.
is why you have to test these things at every step. And it's really tough. Like, it's tough when you're doing a port because you don't know how much you need to test it. If you're doing something that you know how to do, you'll automatically start breaking things down into testable chunks. Like, you'll see me do on the shows, like, let's see what this does, let's see what this does, let's see what this does. We didn't do this at all this time because I don't know how little or how much we need of this thing to work.
Yeah.
And so it's trickier because of that. You kind of have this per chunk aspect to it. But it is working now, and it's doing what we want. It's getting in our shortest distances, and that's
pretty
freaking awesome.
It's pretty cool.
So, let's see if we can make this thing like a different one.
Yeah,
there we go.
There you are.
Yeah. Awesome.
That's pretty cool. I will say
Totally
that.
awesome. All right, so we have it working. So, it's been an hour. I'm going to spend the next few minutes. I don't think anyone's going to be upset with me. If they are, send an angry email.
Yeah.
So let's make our monster do something now. So we did this just as a debugging purpose. I'm going to leave it in, but I'm going to go ahead and turn off the goal on our node 1 here so that it doesn't render. We just really had that for a test case. We could remove that completely. I'm not going to do it just in case we need another test case in the future. So let's node some things here. So I'm going to move this thing. So let's just start fresh. Let's just kill all these nodes. Delete all these.
Poor
and then
nodes.
we're going to go down here. And this ground is at 0, right? All right. So let's do all our noding at like 1 unit high.
Yeah, you don't want it to be.
It doesn't
yeah.
really matter, but let's go ahead and do that. So we're going to create a empty game object. I'm going to call it node 1. And how are we going to do this? Let's change our level around just slightly. I'm going to take one of these and shrink it a little bit, and move it over to the right, so that we have kind of a pathway out. I'm going to go ahead and make this even bigger than it already was. Let's go 20 by 20. And then since we're doing that, we might as well double these as well, so it actually still has the same feel to the ground.
Mm-hmm.
And let's create a couple. I'm just going to duplicate this, and actually, no. Way too lazy. That requires me to rotate. I'm going to duplicate this, move it out here, and then I'm going to duplicate it again, so that we just have a little hallway type scenario here. We're just mocking it up real quick. I basically want to see if we can get a monster to walk down this hallway and then go to us, even if we're like hiding around this corner here or something.
Yes, absolutely.
So so let's take our node 1. I'm going to go ahead and put this. So we're going to put it at Y1. And then we're just going to place it visually. I'm just going to drag this thing over here. So that's our first node. So I'm going to duplicate it. We're going to move it in here. I'm going to put another node here. I'm going to actually put the... I should have done this beforehand. So, so these have the scripts.
So now you can see the little cube on
So
it.
now you can see the cube, and I'm going to go ahead and start connecting them too. So I'm going to call this one node 2. And we're going to connect node 1 to node 2. And we're going to also back connect it as well. It's not strictly needed for our test, but I'm going to do it anyway. I'm going to duplicate this node again. And we're going to call it node 3. I'm going to move this over here. Actually, let's just do node 3 in the middle of the room. This is not an optimal case. I just want to make sure that it works and just get some very basic stuff in here. So node 3, we actually don't want node 1. I did that again, didn't I? So we want this connected to actual... It is connected to node 2.
Yeah.
But node 3 is connected to
Correct.
node 1. Okay, that's the problem. So we'll just connect this one to node 2.
And node 2 can be connected to node 3 as well. Yeah, that's right.
Yeah, so node 3. So we've got the most stupid example ever here. So now we have to do our AI. So we're going to have to change our zombie AI a little bit. I'm going to hit play and then hit stop so that thing went away.
Yeah.
There was an error there. It has something to do with us asking too much of our nodes before the array is initialized. So it's probably... Actually, I know exactly what the problem was. We could probably fix it by... I'm not going to fix it.
Yeah, it's just not
Basically,
working.
what was happening is it's checking for neighbors, and if neighbors hasn't been set in the editor at all, it'll actually be null. And so it's like, give me the neighbors in null. It's like, wait, what?
There are no neighbors in null.
Yeah, it's like,
it
what are
doesn't
you
know how
trying to
handle
do?
that.
What are you trying to do? So that's the reason we're getting that error. It's really minor. We can get around it. As a matter of fact, we could just check for null, but we're not going to because I want to get this done. So zombie AI. So now, instead of going to the player, we're going to first check to see if we are in the player's node, like if you and the unit share a node. And we're going to define owning a node based on whatever the closest node is to you, or to the object in question. So let's add actually to our player first. Where's our player? Scripts, HP Manager.
Where's
Oh yeah,
player?
the player is just this.
He's
Is
a
a first-person
fellow.
controller, isn't it? So,
Yeah.
so I'm going to actually create a new prefab for the player. Wait, he doesn't have any scripts other than what we've... Okay, so we need a player script. So
Yeah.
I'm just going to add a C# script called player, and it's not going to be very complicated. We're going to throw it on the first-person controller here, and all it's going to have is
It's the node.
you know, actually, let's make it generic. Let's not call it player. Let's just make this... I've changed my mind. We're going to call this current node. And that's all it's going to contain is... It may have some logic in it, but we're going to do current node. And all this contains is public game object current node. And then we're going to have it determine what the node is that the object has. So we're going to just set, it's not going to be set to anything at first, and then at start we're going to set it to whatever the closest node is. So for each, it's going to actually be very similar to our distance check here in Dijkstra. For each game object obj in game object dot find game objects with tag node, and while I am thinking about it, I know for certain that we didn't actually set that up on those nodes.
Oh, that's true.
So let me just do that real quick. Node 1, node 2, node 3 all need to be in node.
Good call.
All
I
right.
would have forgotten about that.
Yeah. That's what I always forget about. So I even have people. I now have people actually noticing errors in my show. So evidently people are noticing us now.
That's good.
Yeah, it's great. Because I get comments. It's like, yeah, I just was holding my breath, waiting for you to tag the damn thing. So we basically check the distance of the object. So we're going to do float shortest distance equals mathf dot infinity. I said this is going to look similar. And game object. Actually, we'll just set the current node to whatever the shortest distance is. So for each game object obj, if obj dot transform dot position minus transform dot position dot magnitude is less than shortest distance, that looks right.
That is.
So if it is, then we set the shortest distance to equal this thing. Let's actually do this on a separate line. So float dist equals, because we're using it twice, I don't want to have to do dot magnitude twice if we can avoid it. I don't do a whole lot of optimizations, but I try to keep from doing extra work when we don't have to. Dist is less than shortest distance distance equals dist. And then current node equals obj. And so effectively this should, as a matter of fact, I'm going to actually put this into a separate function. Void find set current node. Throw all this in here. It doesn't take any variables. It has everything self-contained nicely. And the reason I'm doing this is so we can just do set current node.
And you could theoretically
and we're just going to call it in update as well. And we technically don't need to check this every frame. And we basically only want to care if you've moved out of range or into another range and stuff, but I don't care right now. We're just going to set it like this for now. So now we have a current node. So we can attach this script to our zombie and to our player. So player, which is first person controller.
That one, yeah.
And our zombie. And so if we hit play and look at our zombie, it should have picked a node. So node 3. So it's closest to node 3. Let's see if that actually looks about right. Node 3 is right there, so yeah, it's closest to node 3. It's definitely closer than this one. If we were to move this closer to it, let's see if it becomes node 2. This is just for testing purposes. So now if we go to our zombie, it says node 2.
Yeah.
Alright, so it's working. So if I hit play, it'll undo that change because we were doing it in the play mode, which is what it's there for. I'm going to go ahead and move the zombie to be in a different position. We're going to move it out of its little cage.
You're uncaging the zombie.
I'm uncaging the zombie, and we're going to put it out here. So, so now in the zombie AI, we're going to make it so this will happen if GameObject.get component current node dot current node equals okay, so first let's get the GameObject player equals going to do player here now, and we need to finish this up. So if it equals player dot get component current node dot current node dot current node. Autocomplete is your friend.
Yes.
So if it is in the same node area, it will seek us out. So this is our seeker behavior once you, so if the dude is in the same node as the player, chase player. Else we're going to traverse I want to put this. Traverse to next node in path to player node. So we're going to be using our Dijkstra here. So let's look at how we used it here in Node here real quick. So stack GameObject path. We're just going to grab this whole thing, throw it into Zombie AI. So we want so we still want this to be the whole graph, so find game objects with tag node, that we're going to keep that. Our initial node is going to be our current node, so it's game object current node dot current node, and our goal is the player.
Oh, you missed a G. Same
Thank you.
object.
We want lowercase g on that.
Yep.
And then we want the player to be the goal. So player.current node. So this should be our path.
That is a long line of code.
It is a long line of code. And you can, if you want it to be more readable, we could actually do something like this, where we just put enter here, and then we put another enter here.
Oh, that's a little bit more readable, yeah.
Yeah. You can put as many spaces and stuff in things. It's white space independent on C#, so you can get away with this. I haven't done this before. I might as well do it now just so that it's there. You could even do one here, actually. I know some people like that better because it lines them all up, so I'm going to do that. So these are all this is the first component, second component, third component of the Dijkstra method. This is the same as if those spaces were not in there. So
looks a little less intimidating that way.
Yeah, I think so too. Maybe, I don't know. It's new format. So,
Yeah.
so the next one. So the path. I forget the path contains the current node. I'm going to assume that it does not. So we want to pop. We actually really only care about the next node in the path. We don't care about the whole path.
Correct.
But we have it here, so I don't care about that right now. So we're just gonna pop path.pop. Come on, autocomplete. Oh, wait, no, that's right. Path dot. Path dot pop. Whatever. Pop.
Oh, it doesn't have using system
thank you.
collections generic.
Thank you. You were totally right. It doesn't know what the heck a
it's just
path
like,
is.
what are you doing, man?
Dot collections dot generic.
And now it will know what a path is.
So now we can do path dot pop.
There you go.
So this just gives us the top thing on it, which should be the next node in the list. So this game object goal equals path.pop. And then, so we're going to just basically do exactly the same stuff we do here. Just going to copy and paste this whole chunk. And we're going to just rename a couple of these things. So we're going to do goal position, goal direction. So this uses goal position, and then goal direction.
Don't forget to change the goal position.
I need to change that in a second. We'll get to that in a second. Normalize goal direction. And then rotate towards, normalize goal direction. There we go. So, and then we need to actually set this instead of player.transform.position, it will be goal.transform.position. All right. Let's see if it works. Let's see if the first try we get everything working. So first of all, let's see if we got any. We didn't get any compilers.
That's always a good sign.
So I'm going to hit play. And I'm going to run over to this corner here, and I'm going to see if that monster comes around that corner. And if it does everything right, he should come around that corner and actually start going towards that center node. And as soon as he's closer to that center node than he is that node, he will. Can I actually see through that corner here? Maybe I should pause it and
make sure he's actually moving.
Let me just do this. He's moving.
And there he goes.
Oh, and okay, so he is actually working. We didn't do everything exactly right. So if we watch him here, he starts moving towards this second point here. Now the thing is, he's going to get at here, he's going to be closer to this point than he is to this point, and then he will be owned by this point. So he's going to be grinding into the wall here along the ways here for a little while. Which we could fix by just more nodes and being more careful about that, or we could change the way that the methodology. So at this halfway point, you'll see he's now turned towards that node. And so once he gets closer to that node than us, he should path. So as I said, he's bumping and grinding.
He's definitely grinding. Come on, dude.
So
there he goes. So once he gets closer to that other node, he should focus on you.
Yep. And then he'll start going towards me. And then if we run down that hallway, he should figure that out too. Which we're going to do as the second part of the test. Can you see this okay? Is this big enough?
Kind of small, but...
Here, let's focus
there
on
we
the
are.
zombie. Alright, so he's definitely close enough there. Where's my player?
Where's your player?
Oh. Why am I near the...
I don't know why you
I
were
got
near the
reset
node.
for some reason.
That's very strange.
Okay, well, I did, but that's weird. Alright, so,
Let's run
So,
down
yeah.
that hallway.
let's run down that hallway. That's a good test. So, he's following us, he's following us, he's following us, he's following us, and as soon as we get owned... Okay, he stopped following us, you saw that.
Yep.
He now is trying to get to that node that we're now owned by, and we're going to be owned by this node as soon as we're done down this hallway. So there he goes. You can actually see him through the wall because I've got him selected there. Let me get rid of these stats. So you can see him moving there.
Mm-hmm.
And he evidently feels like he should be going towards this node now. I think our noding's bad, but I think the logic's right. So I'm going to call this a success. Went on a little bit longer than usual, but yeah. So that's very basic pathfinding. We'll fix bugs and make it nicer and make it more user friendly in the next episode. So
as always.
So thank you very much for watching. You can email me at pushypixels@pushypixels.com. My Twitter is @Drakfire.
My Twitter is at magmalemur, and you can email me if you really want to, just to be nice and email me, as philip@protosoftworks.com.
And so buy Proton Pulse. I've got a video of it running on Ouya. We're going to be supporting the Ouya, so if anyone out there actually buys an Ouya when that thing comes out, that's going to be a launch title for it. So
Pretty
it's
cool
going to be
stuff.
It's going to be a different version. Also, Phil, you made an update to your game, right?
I did. It's actually version 1.2 now. I added achievements, game center achievements to my game.
Chivos.
So you can
Chivos.
you can get your Chivos on my game now. It has 18 achievements total, and it's still for the low price of $1. Actually, less than that, it's 99 cents. So if you have an iOS device and you like to support us, that would be great.
Yep.
I don't get paid for doing this. It's just out of the goodness of my heart. It's good stuff.
Yeah, he does it for the advertising, so this is the advertising right here.
Yeah. Well, and because I enjoy learning things, too. Don't take that away.
Yeah.
But yeah, pick up Proton Pulse.
Yeah, pick up automation.
Yeah, absolutely.
And you guys have a wonderful night. We'll see you next week.
Have a great week.